Welcome. We are now in chapter 8, rotational motion. So, up until now, we've been concerned mainly with translational motion or linear motion. In this chapter, we will discuss the kinematics of rotational motion, or sometimes called angular motion, and its dynamics, which involve torque, as we've discussed in chapter 7. So we will also discuss rotational kinetic energy and angular momentum, which you probably heard already from chapter 6. So this is analogous to linear momentum. So we're going to apply the same concept only in terms of rotational or angular. We will be concerned with rigid object again. So that means the object have a fixed axis of rotation. This shape doesn't change, so that's more important. Displacement to which we look at the system or the object might change, but this shape doesn't. So there is a pivot point. So to describe rotational motion, we make use of what we call angular quantities. So we're going to talk about angular quantities to be able to look into rotational motion. So we'll start with angular position or angular displacement. So to be able to measure the angular position, so we'll look at the arc length and the radius. So the ratio of these two is what we call the angular displacement. So that's our angular displacement. So if we say that the object moved from this point to point P, so this P moves to that point right here, we're gonna say there is a change in displacement or angular displacement, which is represented by a symbol theta. So we have a change in that displacement, and the unit is either in degrees, or what we're going to use more often would be in radians, or abbreviated as rad. So that's how we looked. So we review your math geometry. So you have 360 is 1 revolution, which is equal to 2 pi. So in order to find the angle, it's the ratio, the theta ratio of the arc length over the radius. Now let's use a more realistic object here. So let's say if we have a bicycle wheel here that rotates about its fixed point, the axis of rotation, the fulcrum, the pivot point. So it has an initial position. So after some time, it traveled that particular displacement. So we could say that given a displacement in a certain time, we could determine another angular quantities, and that is how fast it's going at that particular time. So we now we refer to it as angular velocity. So angular velocity is represented by the lowercase Greek letter omega. So it's like a cursive U, lowercase. It's a lowercase omega. The uppercase is a unit for a particular physical quantity in electricity. So we have that. So the angular velocity is equal to the change in theta or displacement over change in time, and the unit would be rad per second. And also take note, we could determine the theta, the displacement, That's the angular displacement or position. So take note, we notice here that the angular velocity is independent of the radius. So it don't matter, the angular velocity would be the same all throughout. So it don't matter, it's right here, it's right here, it's right here, the angular velocity will be the same. It does not, it disregards the radius of this system. So that's something you have to look into. So we know that every point in an object that is rotating has an angular velocity. However, as it rotates around a circular path, there is also translational motion in here. So in a rotating object, there is angular velocity and there is also linear or translational velocity. So these two are different. So with linear, we know that the velocity linearly is a change in the length over change in time. So the unit for length is meter, the unit for time is second. However, it also is possible in a rotating object, so there is angular velocity there. But if you will notice, this object B here travels from this point to that point. Object A travels from this point to that point, which is closer to the axis of rotation. You will notice that the arc lengths are different. So if you look at linearly, whoever has the greater displacement that's directly proportional to the velocity would mean will travel in terms of the higher speed. So this one, the object on the outer edge, have a higher linear speed compared with the one inside. So if you're in a merry-go-round, the one on the edge, if you're out on the edge, you have a greater speed than the person that is closer to where the axis of rotation is. Now we could relate this to this translational and then this rotational quantity here. So if we are gonna look into to find the arc length, that is equal to the product of the radius and the angle theta, right? If we go back to the previous concept, so we could definitely plug this in here. So we now have velocity, radius, theta over change in time. Now, does this look familiar? Yeah, that is angular velocity. So we could combine the two equations now by plugging this to this. So now we have the linear velocity equation to be equal to the product of the radius times the angular velocity. So we have another equation here. So an object such as the wheel can move or rotate a fixed axis either clockwise or counterclockwise. So if the direction is positive and we choose the angular displacement to be positive when the wheel rotates counterclockwise, and if the rotation is counterclockwise, if the rotation is clockwise, then the angle would decrease. So the change in the displacement would definitely be negative. And in such case, we will also take note that there's a change in the velocity. So if there's a change in the velocity, then another physical quantity or angular quantity will be present, and that's gonna be Yes, acceleration. So we have two acceleration in here, just like the velocities. We have linear, which is tangent from the away from the circle, the rotational motion, the angular motion, and radial. So if we're gonna look at the acceleration tangentially, we know that it is a change in velocity over change in time, and we know velocity based from the previous equation is equal to radius times the angular velocity over change in time. So we're gonna look into that in terms of acceleration angularly. We will now use a different symbol. We use the lowercase alpha, so it's angular change in angular velocity. So final, initial 1 or 2, 0.1 or 2, and then change in time. So we'll have a change angular velocity. So that's our angular or rotational acceleration. Now if we look at this look familiar as this, right? Then we could plug this equation into here. So our tangential acceleration is equal to the radius times the rotational acceleration or radial acceleration. So we could also derive another equation for this. So you have radial acceleration, which is in a circular motion, that's v squared over r, and then knowing velocity too again is equal to radius r, it's right there, squared over r. So we could simplify that. We have radius the square, and the unit would be radian per second squared, and for this our unit would be meter per second squared. So take note of the unit. The unit will tell you this one is translational and this one is angular or rotational. So to sum up the relationship between translational and rotational, so let's look at this table here and take note. This would have radian unit of measurement. So this is the linear motion and this is your angular. So all you're gonna do, so these are all analogous, right? All you're gonna do, as long as the acceleration is held constant, as long as the acceleration is held constant, so uniform acceleration, constant, all you're gonna do is replace the symbol and plug in the appropriate quantity that we use for angular acceleration. Now let's apply some of our understanding on this. So let's use your book, page 311, numbers 1, 2, 3. So take a look at this, press the pause, and then try solving it on your own, and I'm gonna show the solution in this case. See if you did the math right. So solving for the unknowns, this is gonna be your answer. Alright, let's look at another problem, problem number 2. So give yourself a pause and determine what will be the angular velocity for this. So RPM means revolutions per minute. And that's gonna be your answer for this. So take note, angular velocities unit should be rad per second. Now let's consider this problem number 3. So let's solve for acceleration. In this case, you're gonna look for acceleration. So for letter A, you're gonna look for angular acceleration. So final minus initial change in time. So same thing for B. So those are the same equation you're gonna use. And same equations for letter C2 as well. However, for letter D, it's gonna be different. You're gonna be using the tangential acceleration formula in such case. And then for D, so your acceleration tangentially would be radius times the angular. Sorry about that. So your answer should be this. Should be negative. So we cancel that out. Alright, so now it's your turn. So let's solve one more problem. So practice your answer on this, page 311, problem number 8. You should get this answer for letter A. Use this equation for B. You should get that answer to find for change in displacement. And to find for the arc length, use this equation from our previous discussion. You should get 4.5. And that's it for rotational kinematics. So the last section for this chapter would be rotational dynamics.